Good afternoon to all, and welcome to lecture number 9. So in this lecture, we'll be talking about age detection. So first question comes in our mind that what is an age? Okay, why it is so important in computer vision, and then okay, what are the challenges in age detection, and then how to detect it, and so on. And what are the reasons basically how ages are caused in the image and so on. So that we will study in this lecture. So here basically you know that I defined earlier about the spatial frequency. So it is nothing but the rate of change of pixel intensity. So here you see that this image basically all the pixels in this region are having intensity equal to 0, and all the pixels in this region are having intensity equal to 255, right? So the border where there is a change in intensity, so this border is forming the edge. So if you look at this border, basically the rate of change of pixel intensity, so intensity at this pixel is 255, whereas intensity of this pixel is 0. So change, that is difference in the intensity, is large, and so this rate of change of pixel intensity is higher, so it is called as the high spatial frequency. So at the edge there is a high spatial frequency. So you know that a large change in image brightness of a short spatial spatial distance is called as the edge. Like for example, this is suppose, for example, this is the pixel having intensity I of x comma y. This is the location of this pixel, and the just neighboring pixel is having intensity equal to I of x plus dx 1 comma y. So a change in distance, basically this one value of x, either x or y, something like that. And then this difference, if it is large, okay, then this that edge will be having the greater strength and so on. So edge strength depends upon the difference of the neighboring pixel and so on. So edge is nothing but it is having the larger difference at that pixel. Intensity value of that pixel is basically consecutive pixel is larger. So that pixel, corresponding pixel, is considered as an edge pixel. And so we can say that edge is nothing but the high spatial frequency component and so on. Now, this kind of edges, like for example, if there is a sharp change abrupt change in the intensity, so this basically boundary forms the edge. Now, detecting this kind of edges are very, very easy by using simple difference operation, and this difference operation is nothing but it is equivalent to the high pass filter. We have seen in earlier lecture for removing the noise we have used the integration, whereas here in case of detecting the edge we have to use the difference operation. So integration is analogous with your low pass filter, whereas difference is analogous with your high pass filter. So edge can be detected by using simple high pass filtering operation, and detecting this kind of edges are easy because this very sharp change in the boundary, sharp change in the intensity is there. So detecting this sharp change with simple high pass filter is easy. So we can detect this edge very quickly and so on. So this edge is easy to find. But if you look at this kind of edges, like for example, where edge is there, here, or somewhere here, so we don't know. Or if there is a gradual change in the intensity, okay, you see that in this image, second image, there is a gradual change in the intensity. Now here, it is really challenging to find where exactly edge is there. Okay. Here also in the same way. Okay, only thing is that okay, there is a change, but it's not a gradual change, but it's not abrupt change also in this case. So we don't know basically where exactly age is there. Even for human vision system also, it is difficult to detect the age. And also we need basically a age should be detected as a single pixel wide and so on. But here in this case, is it possible to detect the single pixel wide age and so on? So this is really challenging, and you know that this kind of edges are there in many real world application, like for example in the medical application and so on. So simple basically this one high pass filter or a difference operation will not work. We have to use the special techniques like as a scale switch approach or level set approach and so on, or snake approach for detecting this kind of edges. And as I told you that this kind of edges are found in many medical applications in X-ray imaging or so on, so like that way. So this is challenging to detect the age and so on. Now another thing is that if you look at so for example, there is an abrupt change in the intensity, but if your image is corrupted by the noise, and also I explained in my earlier lecture that noise is also a high frequency, high spectral frequency component, and rate of change of pixel intensity at that location is high, and at age also the rate of change of pixel intensity is high. So if you use the high pass filter for using detecting this age, then there are chances that noisy component which are present in the image will be also detected as the age, and then that will lead to false age detection and so on. So we have to take care of this noisy component also while detecting the age and so on. So we have to distinguish noise from the actual age and so on. So there are basically several ways to do to tackle this one. Like for example, canny age detection is technique is there, or generally low pass filtering, image averaging is done before detecting the age and so on. So you can remove the noise, and then after that you can apply the high pass filter which will detect the age. So so that this false age detection can be avoided in that case. Now, what are the different causes of age? Like for example, so this is one texture and this is another texture. So definitely, when there is a change of texture, also there is a change. There is a age border. So this is one of the causes. We can see there are several causes because of change. This one, age is there and so on, right? Okay. Now, why edges are interesting in computer vision? Okay, you will find that the low-level feature in the computer vision are basically formed with the this one, either texture or color or shape. Okay, and out of these three low-level features, shape is one of the important feature, and even human being also recognize the object based on the shape and so on. So shape can be detected by using the edges. Okay, so you can see that shape can be detected by using the edges and so on. So for computer vision also, to make it successful, age is very important component to detect and so on. So edges can or many times represent the information in the image or object. So that is one of the important reason why age is to be detected. So a higher level of abstraction, that is less data to processes. Like for example, instead of processing the entire pixels inside this one, we can process only the edge pixels of this one. So we can say that this is the higher level abstraction, and this will require only the less data, like as only the pixels of edge border and so on. And then we can reduce the computation complexity for this one recognition and then identification and so on. Another thing is that edges are features. So we can extract the edges as one of the important feature in computer vision. So they're independent from the elimination edges are independent, means basically this edge feature does not depend upon the illumination and so on. So as opposed to, for example, color information may change because of changing illumination or lighting condition and so on. But generally, edge information does not change with the illumination. So we can say that we can develop the illumination independent method by using edge features and so on in computer vision. And then another thing is that object recognition and detection. So many times you use edge features for object recognition and detection. So this is true for electronic as well as for biological vision system. As I told you that even our biological vision system, we give more importance to the edge features rather than color and texture features. So same is true for computer vision also. Computer vision also gives more importance to the edge feature compared to the color and texture and so on. So that's why edges are very, very interesting to detect in the computer vision for developing the foolproof method in computer vision and so on. Now, what are the origins of the edge, where edges can be caused? Like, for example, here edges are caused by a variety of factors. Like here there is a surface normal discontinuity. If surface normal discontinuity is there, then there will be edge and so on. So not surface normal discontinuity. Then edge depth discontinuity. If there is a depth discontinuity also, that will form the edge. So this is basically a simple bottle, and then if there is a depth discontinuity, it will form the edge. Even surface color discontinuity. See that if this, suppose for example, this is printed with some kind of color and so on, and if there is a change, this is white color and this is black color, so this will form the edge. So surface color discontinuity will also cause the edge. Now this, look at this one. What is this? This is nothing but your shadow of that one, or illumination discontinuity also is there and so on. So edge, there are several factors of this one, edges. So which are the causes of edges, causes of change in intensity? So if you look at geometric point of view or geometric event, like surface orientation or boundary discontinuity is there, then there will be an edge. If there is a depth discontinuity, there will be edge. If there is a color discontinuity, there will be edge. If there is a texture discontinuity, there will be edge. So these are basically, this comes under the geometric events or discontinuities and so on. Whereas non-geometric event, like for example, if there is an illumination change, or if there is a shadow, if there is a specularity or enter reflections are there, so that will also form the edge. Means basically, if you look at the reasons of this edge, like first one is surface orientation or boundary discontinuity, then depth discontinuity, then color discontinuity is there, texture discontinuity is there, illumination changes will also call the edge, then specularity is also called the edge, shadow will also call the edge, and then this one, enter reflections will also cause the edge and so on. So there are 8 to 9 different reasons why there is the edge in the object and so on, why edges are formed in the object and so on, right? So depth discontinuity, that is surface. Sometimes also, for example, if there is a occluded surface, like one object is occluded by the other object, like for example, like this way, so that will also cause an edge. Or surface orientation discontinuity, or reflectance discontinuity, or texture or color changes, or illumination discontinuity like shadows and so on. So these are the various reasons why edges are caused and so on. Now look at this one. Basically, if you see the image, how we can detect the edges and so on. So like for example, if there is a depth discontinuity, if this board is there and then there is a depth discontinuity, then there will be a change in basically intensity values, and then that will cause the edge. You might have seen that. Okay, if you take the picture of your own room and then see that even basically this one, okay, in your room, like for example, this one, your walls are there, and suppose for example walls are like this, so there is a surface orientation discontinuity. So though those walls are painted with the same color, but you can see the edge in the corner because there is a surface orientation discontinuity. Or even for ceiling also, you will find that there is a age and so on, because there is a surface orientation discontinuity. So reflectance discontinuity. So this is nothing but the surface orientation discontinuity. So this age can be found because of surface orientation discontinuity, or reflectance discontinuity, that is change in surface material properties, will also call the age, or illumination discontinuity, that is nothing but the shadow. See, look at this one. This is the basically a tree, and then there is a shadow of this one. So this shadow will also form the age. So as I told you that there are 8 to 10 reasons why edges are formed in the image and so on. Now we have to detect all those edges by using computer vision method and so on. What is edge detection? Basically, you can look at this one. So this is a image of this one. 5 by 4 size, right? 5 rows are there and 4 columns are there, and these pixels are having intensity equal to 0, whereas these pixels are having intensity more than this one. So definitely there will be an edge like this in the image, because there is a high rate of change of pixel intensity here. So high special frequency component will occur, and then you will get the edge component like this in the image, right? So edges are formed in the image because of high special frequency component. Now, question is that how we can detect the edges in the computer vision. So the input, basically, we have seen that the image blurring is accomplished in the spatial domain by pixel averaging in a neighborhood area, or while either image blurring or removing the noise, we can use the averaging filter, mean filter, or something like that, or even nonlinear filter we have seen in last lecture, that is nothing but the median filter. So since averaging is analogous to the integration, so this was used only for removing the noise. But now either you have to sharpen the image, or you have to basically find the high special frequency component. So high special frequency component means basically the difference of the consecutive pixel must be, this intensity difference must be high. So you have to use the differentiation operation. So differentiation is nothing but the derivative. So sharpening could be accomplished by a spatial differentiation or derivative. So here, as I told you that noise is removed by integration operation, whereas edge is detected by using the derivative operation. If you take the derivative of this one, so derivative in the digital image is nothing but taking the differentiation or difference of the consecutive pixels. So we are interested in the behavior of these derivatives in the area of constant gray level, like for example, flat segments, or at the onset and end of the discontinuities, that is step, or sometimes you can get the ramp discontinuities, and also along the gray level ramps and so on. So we have to find out the edges in such situations and so on. So these types of discontinuities can be noise points. Sometimes, as I said, that there may be a false edge because discontinuity may occur because of noise, or discontinuity may occur because of lines, and discontinuity may occur because of edges. Okay, so we are interested to find out all those things, and we have to basically, for ideal edge detection, it should be noise free, means there should not be any false edge. It should be one point. There should not be multiple points of edges, and so on. Means 1 pixel thick edge should be detected, and then it should be the actual edge. It should not be like okay, edge is somewhere and you have detected at somewhere and so on. So the location should be correct. Edge thickness should be 1 pixel wide, and it should avoid the false edges. So these are the 3 important things while detecting the edge. So we'll see in our due course of time that how edges can be detected and so on. So basically here, this one, age detection filters are used like as a high pass filter, which eliminates the uniform region. That is means when uniform region is nothing but the low spatial frequency. So when you pass this one through the high pass, so definitely this this one uniform region will be eliminated, and you will get only, or low frequencies will be eliminated, and you will get only high frequency component. That is nothing but the edges which will be detected, and so on. So age detection or enhancement can be done by using the high pass filtering operation. Now when you are designing the high pass filter, there are basically certain criteria, like whatever the kernel you can select, either the kernel size maybe, as I discussed in my first lecture of this chapter, for doing this filtering you have to use the kernel or window, or you have to use the sub image, something like that, which I explained. Now here we are going to use the kernel which is of high pass filter, and the first property of this one is basically the kernel coefficient should be the sum of the kernel coefficient should be equal to 0. In case of this average filter, you know that average filter 3 by 3, what was the intensity values? That was 3 by 3 was 1 1 1 1 everywhere, 9 points were there, and then 1 1 1 value was there, and then divided by 9. So if you take the average of that one, that will be equal to 1. But now here the kernel coefficients, if you take the summation of this kernel coefficient, that summation is equal to 0 in case of difference or high pass filter, whereas in case of low pass filter this summation is equal to 1, right? So this is the first difference between the low pass filter and the high pass filter kernel. So sum of kernel coefficient is 0 in case of high pass filter. Another thing is that differences in the sign emphasizes difference in the pixel values here, right? Another thing is that in high pass filter it reduces the average image intensity, right? And then sometimes it may happen that negative pixel values may be there in the output, so you have to take care of that one by taking the absolute value and so on. Now, as I told you that this can be detected by taking the derivative. So you can take the first derivative, you can take the second derivative, and so on. So what is the basically definition for the first derivative? So first derivative, it must be 0 in flat segment. So when you take the derivative, it must be 0 in the flat segment, means low spatial frequency component should be eliminated by using the first derivative, and it must be non-zero at the onset of gray level step or ramp, means if there is basically a gray level step function is there, or if there is a ramp kind of function, means your age is gradually changing or pixel intensities are gradually changing and so on, then in that case whatever the difference first derivative you will get, it will be non-zero. So it must be non-zero at the onset of gray level step or ramp and so on, and also it must be non-zero along the ramps. Okay, so these are basically this is the requirement of the first derivative and so on. Then second derivative, now when we are going to use the first derivative and when we are going to use the second derivative, that I'll explain in my next lecture. If you take the second derivative is nothing but, like for example, once you take that first derivative of the image, again if you take the derivative of that image, you will get the second derivative. So it must be 0 in the flat area. So if you take the second derivative, it must be 0 in the flat area, and it must be non-zero at the onset of end of gray level or step or ramp, and it must be 0 along the ramps of constant slope and so on. So this is the, see that in case of first derivative for ramp 1 it was non-zero, but here second derivative because see that ramp, if it is ramp is having the constant slope, so definitely if constant slope is there, second derivative will be equal to 0 in that case. Okay, now what is the use of this first derivative filter and what is the use of second derivative filter? As I told you that I'll be explaining in detail about this one in my next lecture. So if you look at the first derivative, first order derivative. So simple basic definition of the first order derivative of one-dimensional function is given by, what is this? We are taking the partial derivative with respect to x of the given image f of x comma y. Now what you are doing, this is the intensity of x plus 1 pixel, and we are subtracting that intensity value of f of x from the f of x plus 1. So next intensity, the current intensity value will be subtracted from the next intensity value of that row or either that column. If you are basically operating on the rows, then definitely this is the current pixel and this is the second pixel. Then a derivative will be taken that this pixel intensity minus this pixel will indicate as f of x plus 1, this pixel will indicate as f of x, and so on, right? Now second derivative, what we are doing, we are taking the derivative of that derivative, or derivative of this first derivative, right, with respect to x only. So dou 2f by dou x2 is given by f of x plus 1 plus f of x minus 1 minus twice of f of x. So this will be the equation of second derivative as a second difference, and so on, right? Now if you see the gray level profile of this image, like for example, this pixel is having intensity equal to 0, this pixel is having intensity equal to 0, this pixel is having intensity equal to 0, then this one is having intensity equal 1, 2, 3, 2, 0, 0, like that way. Now this is the intensity of this pixel as a 7, whereas 6, 5, 5, and 3. Now if you look at the gray level profile, like for example, this is nothing but basically corresponding pixel, and this is the intensity on y-axis, intensity on x-axis, pixel, corresponding pixel. So this is the gray level profile. Like for example, just you have plotted the intensity value in the gray level profile. So first pixel is having equal to 0, second pixel is having equal to 0, third pixel is having intensity equal to 0, fourth one is 1, so this is 1, then fifth one is 2, so this is 2, sixth one is 2, seventh one is 3, and seventh one is 2, and so on. So like that way you have plotted this sequentially, right? So here on x-axis, this is nothing but the pixel number, and on y-axis, what is its corresponding gray value, and so on. So this is called as the gray level profile. Now if you take the first derivative of this gray level profile of this image, how it will be, or like that. So this is the gray level profile of the image, like 0, 0, 1, 2, 3, 2, and so on. So this is whatever we have detected, this value we have taken as a gray level profile. And then what is its first derivative and what is its second derivative? So you know that first derivative, this difference, just by taking f of x plus 1 minus f of x. So this is the first derivative. Then this one, say 0 minus 0, this is 0. 0 minus 0, it will be 1. 1 minus 0, this will be 1. 2 minus 1, this will be 1, and so on. So like that way you got up to this you got up to this one. So definitely what will be this one? Last one, 3 minus 5, that is equal to minus 2, right? Now second derivative of this one, what you have to do, we have to take the first derivative, and then again you have to take the again one more time derivative of this per derivative, so you get the second derivative. So what is this one? So 0 minus 0, this will be equal to 0. 1 minus 0, that is equal to 1. 1 minus 1, that is equal to 0. 1 minus this one, basically 1 minus 1, that is equal to 0, and so on. Now look at this one. See that as we have studied in the first derivative and second derivative, see that if you look at this age, see that age profile was like this, 0, 0, 0, and then it was increased from 0 to 1, 1 to 2 here, 2 to 3. So this was having constant slope with like as a ramp function with a constant slope. But in this case, basically for first derivative, this first derivative was non-zero in this case. But if you look at this one, second derivative, so second derivative is a 0 if there is a constant slope. See that what is the slope of this one? 1. Here, what is the slope of this one? It is also 1. That is 2 minus 1 is 1. 3 minus 2 is also 1. So this slope, first derivative is nothing but the slope. So this is constant. If constant slope is there, so it will give you the 0 value in case of second derivative and so on. So I hope that you have understood how to take the first derivative and the second derivative of the image profile or gradable profile. So you got these values of this first and second derivative. So just what you are done, while taking the first derivative, we have taken the next pixel, intensity of next pixel minus first pixel, that is equal to 0. This one minus this one is 0. 1 minus 0 is 1. 2 minus 1 is 1. So like that way, 3 minus 5 is equal to minus 2. So we have done this one for first derivative. Again, for taking the second derivative, we have to take the derivative of the first derivative. So 0 minus 0, that is 0. 1 minus 0, that is 1. 1 minus 1, 0. 1 minus 1, 0. Then minus 1, minus 1, that is equal to minus 2. Minus 2 minus 1, that is equal to minus 1, and so on. So like that way, here minus 2 minus 0 is equal to minus 2. So you got this second derivative of given age profile, and this is the first derivative of the given age profile, and so on. Now, for detecting the age, basically, how would you go about detecting the edges in the image? That is, for example, if there is a discontinuity in the function, so you have to take the derivative. So derivatives are large at discontinuities. And second question is that how do you differentiate a discrete image or any other types of signals? So you have to define, you have to use the finite differences in that case, and so on. So finite difference, basically, you know that the high school reminder definition of that derivative using the straightforward difference, that is f dash x is equal to limit h tends to 0. And what you're doing, so f of x plus h minus f of x, so divided by h. Now here, in case of image, discrete image, we are taking the value of h as equal to 1. Okay, h as equal, because consecutive pixels are, okay, just differ by one value. So here we have taken the value of h. So you will get the same formula, whatever we have studied in the first derivative. That is, this is the standard formula for the difference f dash x of f of x. There's nothing but the first derivative of x, which is given by limit h tends to 0, f of x plus h minus f of x, and then this h. So this h is nothing but the step size. So step size, in case of detecting the edges, step size we take as a 1. So the value of h is equal to 1. So if it is 1, so this can be neglected. Denominator can be neglected because it is divided by 1. And this f of x plus 1 minus f of x. So which we got the same formulation for this one. Okay. Similarly, we can have the alternative differences also, like as for example 0.5h minus f of x minus 0.5h divided by h, for the use central difference theorem, or using the definition of derivative using forward difference. That is earlier whatever we have seen. This is by using central difference. You get this formulation. And for a discrete signal, remove the limit and set h is equal to 2. So basically you will get the f dash x is equal to f of x plus 1 minus f of x minus 1 divided by 2. So what convolution kernel does this corresponds to? We will see, because we have the kernel size like as a 1 by 1 or 2 by 2 or 3 by 3 and so on. So like that way. So well-known kernel functions which are used in detecting the edges are Sobel operator or Prewitt operator or Krish operator and so on. So how those values are derived from this definition, so we can see all those things. So you know that for this one, if you look at this formula, like for example, if you set the h equal to 2, okay, then this is f of x plus 1 minus f of x minus 1. Means what we are doing, basically we are for finding the intensity or difference at that value, either we are considering the next and the previous one. Okay, next pixel value intensity. See, this is nothing but the next pixel value. So f of x is the pixel under consideration, and for that, what we are doing, we are finding the difference of f of x plus 1 minus f of x minus 1, and then divided by 2. So here step we have used as a 2 here. So 2. See that whether this is really this one representing this one or not. So we'll see a lot on and so on. So like for example, this is equivalent to this kind of filter, 1D filter. Like this is 1 and this is minus 1. Okay, 1 and minus 1. So here the Sobel operator, whatever we get, is this one. See that 1, 2, 1. These are the coefficients of this kernel function of Sobel operator, and 0, 0, 0. And then minus 1, minus 2, and minus 1. So this is the pixel under consideration, and the step size is like, for example, we are taking the difference of this minus this. So step size is 2. This minus this minus this, and so on, right, that way. So this can be obtained like by taking the multiplication of 1 to 1 this vector, and then this row vector and this column vector. So 1D filter, this is also a 1D filter, and then this is nothing but basically blurring, and this is nothing but the derivative. So in 2D image, does this filter response along the horizontal or vertical lines? Basically, if you see this Sobel operator, I think we'll take in detail all those operators, like as a Sobel operator, and then Privet operator and Krish operator, and so on. So in detail in our next lecture, and then after that we can see the Laplacian of Gaussian and this one. Difference of Gaussian operation, and then at the end means maybe in a third lecture we'll take the Canadian detector and so on. So here to summarize the today's lecture, it was basically we have studied with like for example, what is the age, what are the reasons why ages are there. There are 10 different reasons why ages are there, and then how to detect the age, and then what is this high pass filtering, and then difference operation, and so on. And then after that, how those age filters can be derived. So that we'll study in tomorrow's lecture. So today we'll stop here. So thank you very much for this lecture.